You're standing in your backyard on a clear night, gazing up at the stars scattered across the velvet darkness. That pinprick of light you see there might be Proxima Centauri, our nearest stellar neighbour. It looks close enough to reach out and touch, doesn't it? But here's what will absolutely blow your mind. If you could somehow travel at the speed of light itself, racing through space at 186,000 miles per second, it would still take you over 4 years just to reach that single dot of light. 4 years of traveling faster than anything with mass can possibly go, according to everything we know about physics. Now imagine trying to leave not just our neighborhood, but our entire solar system behind. Suddenly, that romantic notion of becoming an interstellar species starts to feel less like science fiction and more like an impossible dream. But is it really impossible? Or are we simply limited by our current understanding of what's achievable? Tonight, we're going to embark on a journey that pushes against the very boundaries of human ambition and scientific possibility. We're going to explore whether humanity will ever truly break free from the gravitational embrace of our sun and venture into the vast cosmic ocean that separates us from other worlds. This isn't just a question about rockets and fuel. It's a question about the fundamental limits of physics, the ingenuity of human engineering, and perhaps most importantly, our species' willingness to commit to projects that span not just decades, but potentially centuries or even millennia. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Let's start. What I'm about to share with you will challenge everything you think you know about space travel. We'll discover why the distances between stars aren't just large, they're so incomprehensibly vast that they redefine what we mean by the word impossible. We'll examine the cutting-edge propulsion technologies that might actually give us a fighting chance, from solar sails that ride on starlight itself to fusion rockets that could theoretically reach 10% the speed of light. And we'll confront the uncomfortable truth about what it would really take, not just technologically, but socially and economically, for our species to take its first tentative steps beyond the solar system. But here's what makes this exploration truly fascinating. While we're asking whether we'll ever leave our solar system, we're also discovering that the very act of trying to answer this question is revealing profound truths about the nature of our universe, the limits of human capability, and what it might actually mean to become a truly cosmic civilization. The scale of what we're discussing tonight is so vast that our everyday experience provides no frame of reference for understanding it. When we talk about interstellar distances, we're not just talking about something far away, we're talking about distances so large that they challenge the very concepts of journey and destination. To understand why leaving our solar system represents perhaps the greatest challenge our species has ever contemplated, we need to first grasp just how alone we really are in this corner of the galaxy. Our solar system, this collection of planets, moons, asteroids, and comets that orbit our sun, extends roughly 100,000 astronomical units from its center. That sounds like a lot until you realize that the nearest star system, Alpha Centauri, lies about 270,000 astronomical units away. In other words, the gap between our solar system and our nearest neighbors is nearly 3 times wider than our entire solar system itself. It's like living in a house in New York and having your closest neighbor living in Los Angeles, except the ratio is actually much, much worse than that. This isolation isn't just a matter of distance. It represents a fundamental barrier that no human technology has ever come close to overcoming. The fastest spacecraft we've ever built The Parker Solar Probe reaches speeds of about 430,000 miles per hour when it's diving close to the Sun. That sounds incredibly fast until you do the math and realize that at that speed, it would take over 6,700 years to reach Proxima Centauri. That's longer than all of recorded human history. We're talking about a journey that would span roughly 270 human generations. But the challenge isn't just about speed. It's about the fundamental physics of acceleration, energy, and the resources required to sustain a journey across such incomprehensible distances. When we start to seriously examine what it would take to send even a small probe to another star system, we quickly discover that we're not just pushing against engineering limitations. We're bumping up against the basic laws of physics themselves. Consider what happens when you try to accelerate any object with mass to a significant fraction of the speed of light. Einstein's special relativity tells us that as you approach light speed, the energy required to accelerate further increases exponentially, approaching infinity as you near the speed of light itself. This isn't just a technical hurdle we might overcome with better engineering. It's a fundamental feature of how our universe works. Mass simply cannot be accelerated to the speed of light, no matter how much energy you throw at the problem. This means that any realistic interstellar journey must be planned around speeds that are substantial fractions of light speed, but still far below that ultimate barrier. Even if we could somehow build a spacecraft capable of reaching 10% the speed of light, something that would require revolutionary advances in propulsion technology, the journey to our nearest stellar neighbor would still take over 40 years. That's longer than most human careers, longer than many human lives. And here's where the challenge becomes not just technical, but profoundly human. Who builds a machine designed to operate flawlessly for 40 years without any possibility of repair or maintenance? Who commits the resources necessary to fund such a project when none of the people making that decision will live to see its completion? Who volunteers for a one-way journey to a destination they'll reach only if they're lucky enough to live to old age? These questions point to something deeper than technological barriers. They reveal that leaving our solar system isn't just an engineering problem. It's a civilizational challenge that forces us to think in timescales and commit to goals that stretch far beyond individual human lifespans. It requires a kind of species-level patience and determination that we've rarely demonstrated in any other context. But perhaps the most sobering aspect of interstellar travel is what we might call the tyranny of the rocket equation. Every pound of payload you want to send to another star system requires fuel to accelerate it. But that fuel itself has mass, which requires additional fuel to accelerate. And that additional fuel requires even more fuel, creating a cascade of requirements that grows exponentially with the desired final speed. The numbers become staggering very quickly. To accelerate even a small probe to 10% of light speed using conventional chemical propulsion would require more fuel than exists in the entire solar system. Even with theoretically perfect fusion rockets, converting matter directly into energy with 100% efficiency, the fuel requirements remain enormous. We're talking about engineering projects that would dwarf anything humans have ever attempted by factors of millions or billions. This is why serious discussions of interstellar travel inevitably lead to concepts that sound like science fiction. Solar sails that catch the pressure of starlight itself, fusion ramjets that scoop up interstellar hydrogen as fuel during the journey, antimatter rockets that annihilate matter and antimatter to produce pure energy, breakthrough Starshot-style projects that use powerful lasers to accelerate tiny probes to relativistic speeds. Each of these approaches attempts to sidestep the rocket equation in different ways, but each comes with its own seemingly insurmountable challenges. Solar sails, for instance, can theoretically accelerate without carrying fuel, but they're limited by the decreasing intensity of sunlight as they travel farther from the sun. Fusion ramjets could potentially gather fuel during the journey, but they require fusion technology that we haven't yet mastered, and the interstellar medium is far thinner than early proponents hoped. Antimatter rockets offer the highest possible energy density, but producing and storing antimatter remains one of the most expensive and technically challenging processes humans have ever attempted. Even the most optimistic projections for these advanced propulsion concepts suggest that true interstellar missions remain decades or centuries away from being technically feasible. And that's assuming we solve not just the propulsion problem, but also the equally daunting challenges of communication across interstellar distances, spacecraft reliability over multi-decade journeys, and the enormous economic and political coordination required to sustain such projects. Yet despite these seemingly impossible barriers, something fascinating is happening in the world of space technology and exploration. The same revolutionary advances that are making space more accessible closer to home are also opening up new possibilities for interstellar exploration. Private companies are driving down launch costs by orders of magnitude. New materials and manufacturing techniques are enabling spacecraft designs that would have been impossible just decades ago. Artificial intelligence is reaching levels of sophistication that could enable truly autonomous interstellar probes. Most intriguingly, our understanding of the universe itself continues to evolve in ways that might reveal new approaches to the interstellar challenge. Discoveries about the nature of space and time, about quantum mechanics and the fundamental structure of reality, about the prevalence of potentially habitable worlds around other stars. All of these are reshaping how we think about humanity's cosmic future. The question of whether we'll ever leave our solar system is really asking whether we're capable of becoming something more than we are today. It's asking whether we can develop technologies that transcend our current limitations, whether we can organize ourselves socially and economically around goals that extend far beyond individual lifetimes, and whether we can find the motivation and resources necessary to take on challenges that dwarf anything in human history. The answer to that question isn't just about rockets and physics. It's about who we are as a species and who we choose to become. And as we'll discover, the very process of seriously attempting to answer this question is already changing us in profound and unexpected ways. The most remarkable thing about humanity's relationship with interstellar travel is that we're already taking the first steps, even though we don't fully realize it yet. Right now, as you're listening to this, there are 5 human-made objects racing away from our sun at speeds that will eventually carry them beyond the gravitational influence of our solar system. Voyager 1 and Voyager 2, launched in 1977, have already crossed that invisible boundary and entered interstellar space. Pioneer 10 and 11, along with New Horizons, are following behind them on their own one-way journeys into the cosmic void. These spacecraft weren't designed as interstellar missions. They were built to explore the outer planets of our solar system, but their trajectories and the speeds they achieved during their planetary encounters have turned them into humanity's first, albeit unintentional, ambassadors to the stars. They're traveling at roughly 35,000 to 40,000 miles per hour, which sounds impressive until you realize that at these speeds, it would take them tens of thousands of years to reach even the nearest star. But here's what makes these missions so significant. They've proven that we can build machines capable of operating in the harsh environment of interstellar space. Voyager 1, after more than 4 decades of travel, is still sending back data about the conditions it encounters in the space between stars. Its instruments are revealing that interstellar space isn't the empty void we once imagined, but a complex environment filled with magnetic fields, cosmic rays, and particles that create conditions unlike anything we experience within our solar system. This knowledge is crucial because any future interstellar mission will need to survive in this environment for decades or centuries. The Voyager missions are teaching us what that environment is really like, what kinds of challenges a true interstellar probe would face, and what technologies would be needed to survive the journey. But perhaps more importantly, these missions are proving something about human nature itself. We are a species that builds things designed to outlast us. We create projects that we know will never see completed, driven by curiosity and ambition that extends far beyond our individual lifespans. The scientists who designed the Voyager spacecraft knew they would likely be retired or gone by the time these probes reached interstellar space. Yet they built them anyway, and they built them to last. This capacity for long-term thinking, for investing in futures we won't personally witness, might be the most important trait we possess when it comes to interstellar exploration. Because make no mistake, any serious attempt to reach another star system will require exactly this kind of multi-generational commitment. The engineering challenges alone would span decades. Consider what it would take to build even the smallest interstellar probe capable of reaching 10% of light speed. The energy requirements would necessitate either revolutionary advances in propulsion technology or engineering projects on a scale that dwarfs anything humans have ever attempted. We're talking about space-based infrastructure that could take decades to construct, requiring international cooperation on a scale that makes the International Space Station look like a modest collaboration. Some of the most promising concepts for interstellar missions involve technologies that don't even exist yet in practical form. The breakthrough Starshot initiative, backed by luminaries like Stephen Hawking and Yuri Milner, proposes using powerful ground-based lasers to accelerate tiny spacecraft, no larger than computer chips, to 20% of the speed of light. These miniaturized probes could potentially reach Proxima Centauri in just 20 years, transmitting data back to Earth about humanity's nearest stellar neighbor. The concept is elegant in its simplicity. Instead of trying to carry fuel for acceleration, you leave the propulsion system behind on Earth and use light itself to push the spacecraft. A massive array of lasers would focus their combined power on tiny light sails, accelerating them to relativistic speeds within minutes. The spacecraft themselves would be marvels of miniaturization, containing cameras, sensors, and communication equipment packed into devices smaller than your smartphone. But even this seemingly straightforward approach reveals layers of complexity that highlight just how challenging interstellar travel really is. The laser array would need to generate power levels comparable to a nuclear reactor, focused with precision that exceeds anything we've ever achieved. The tiny spacecraft would need to survive acceleration forces millions of times stronger than Earth's gravity, then operate flawlessly for 20 years in the radiation-soaked environment of interstellar space. Most challenging of all, these miniature probes would need to communicate their findings back to Earth across 4 light-years of space using transmitters no larger than computer chips. The signals would be so weak that detecting them would require advances in radio astronomy and signal processing that push the boundaries of what's technically possible. Yet despite these challenges, breakthrough Starshot represents something unprecedented in the history of space exploration. It's the first serious funded attempt to develop technology specifically designed for interstellar travel. The project brings together some of the world's leading experts in photonics, materials science, and spacecraft design, all focused on solving the technical problems that stand between us and the stars. But breakthrough Starshot also illustrates a fundamental limitation of our current approach to interstellar exploration. Even if the project succeeds completely, even if we manage to send tiny probes to Proxima Centauri and receive data back from them, we'll still be nowhere close to sending anything resembling a human mission to another star system. The gap between sending a chip-sized probe and sending human beings is so vast that it's almost meaningless to compare them. A human interstellar mission would require life support systems, radiation shielding, artificial gravity, and redundant backups for every critical system. The spacecraft would need to be large enough to support a crew for decades, yet still capable of reaching speeds that make the journey feasible within human lifetimes. This is where we encounter what might be called the human factor in interstellar travel. It's not just about building faster rockets or more efficient propulsion systems. It's about solving the biological and psychological challenges of keeping human beings alive and sane during journeys that could last 40, 50, or even 100 years. The longest any human has spent in space continuously is just 437 days. That's barely more than a year, and it was accomplished with regular resupply missions, constant communication with Earth, and the knowledge that return was always possible. An interstellar journey would require human beings to spend decades in a confined space, with no possibility of rescue, no fresh supplies from home, and communication delays with Earth that would eventually stretch to years. The psychological challenges alone could be insurmountable. How do you maintain morale and mental health among a crew that knows they'll never see Earth again? How do you handle conflicts, leadership transitions, or medical emergencies when there's no higher authority to appeal to and no possibility of evacuation? How do you maintain the technical knowledge and skills needed to operate and repair complex systems across multiple generations of crew members? These aren't just theoretical problems. They're challenges that would need practical solutions before any human interstellar mission could be attempted. Some researchers have proposed that the first human missions to other star systems might need to be one-way colonization efforts, with crews committed from the beginning to establishing permanent settlements rather than returning home. Others have suggested that the solution might lie in developing technologies that extend human lifespan dramatically, allowing individuals to survive journeys that would currently span multiple generations. Still others propose that artificial intelligence might need to reach levels of sophistication where AI systems could serve as permanent crew members, providing continuity and expertise that human crews might not be able to maintain over such long journeys. But perhaps the most intriguing possibility is that human interstellar travel might not require us to solve the journey problem at all. Instead of sending people on decades-long voyages through space, we might eventually develop technologies that allow us to transmit human consciousness itself, uploading and downloading minds across interstellar distances at the speed of light. This might sound like pure science fiction, but the underlying concepts are being seriously explored by researchers in neuroscience and artificial intelligence. If we can eventually understand consciousness well enough to map and replicate it in artificial systems, then interstellar travel becomes a matter of information transfer rather than physical transportation. Imagine being able to scan your brain, transmit that information to a destination star system, and reconstruct your consciousness in an artificial body that's waiting for you there. The journey would still take years for the signal to travel, but from your perspective, you'd simply close your eyes on Earth and open them around another star. These possibilities push us into territory where science and philosophy merge, where questions about the nature of consciousness and identity become as important as questions about propulsion and engineering. They suggest that the answer to whether we'll ever leave our solar system might depend as much on advances in our understanding of the mind as on advances in rocket technology. What's becoming clear is that interstellar travel, in any form, will require us to become fundamentally different from what we are today. Whether through technological enhancement, artificial intelligence, or entirely new approaches to consciousness and identity, The humans who eventually reach other star systems may be as different from us as we are from our ancestors, who first looked up at the stars and wondered what lay beyond. And yet, despite these seemingly impossible challenges, something extraordinary is happening right now that's changing the entire conversation about interstellar travel. We're discovering that we might not need to solve all these problems at once. Instead of thinking about interstellar travel as one massive technological leap, we're beginning to understand it as a series of incremental steps, each building on the last, each making the next step possible. The revolution is already underway in ways most people don't realize. Private companies are launching rockets at costs that would have been unimaginable just 20 years ago. SpaceX has reduced the cost of getting to orbit by more than 90%, and they're not done yet. Blue Origin, Virgin Galactic, and dozens of other companies are pushing the boundaries of what's possible with space technology. But more importantly, they're proving that space exploration doesn't have to be the exclusive domain of government agencies with unlimited budgets. This democratization of space technology is creating opportunities that simply didn't exist before. When launch costs drop from tens of thousands of dollars per kilogram to hundreds of dollars per kilogram, entirely new categories of missions become feasible. We can afford to be more experimental, more ambitious, more willing to take risks on technologies that might fail. And that's exactly what we need for interstellar exploration. Because the truth is, we're not going to solve the interstellar travel problem with one brilliant breakthrough. We're going to solve it the same way we've solved every other impossible challenge in human history. One small step at a time, building on each success, learning from each failure, gradually pushing the boundaries of what's possible until the impossible becomes inevitable. Consider what's happening with propulsion technology right now. Ion drives, once purely theoretical, are now routinely used for deep space missions. Solar sails have been successfully tested in space. Fusion research is making genuine progress, with multiple private companies claiming they're on the verge of breakthrough. Each of these technologies brings us one step closer to the kind of propulsion systems we'll need for interstellar missions. But it's not just about the technology. It's about developing the institutional knowledge, the manufacturing capabilities, the testing facilities, and the human expertise that will eventually make interstellar missions possible. Every Mars mission teaches us something about long-duration spaceflight. Every asteroid mining venture develops technologies for autonomous operations in deep space. Every satellite constellation teaches us about coordinating complex systems across vast distances. We're essentially building the infrastructure for interstellar exploration without fully realizing it. The same technologies that will make us a true spacefaring civilization within our own solar system are laying the groundwork for eventually venturing beyond it. The space economy that's emerging around Earth orbit, lunar exploration, and Mars colonization is creating the industrial base that could eventually support interstellar missions. But perhaps most importantly, we're developing something that might be even more crucial than any specific technology. We're developing the cultural and social frameworks for thinking in really long-term scales. The companies and organizations working on Mars colonization are already grappling with projects that span decades. They're learning how to maintain institutional continuity across leadership changes, how to fund projects with uncertain timelines, how to motivate people to work toward goals they might not live to see completed. These are exactly the skills we'll need for interstellar exploration. Because regardless of what technology we eventually use to reach other stars, the projects will require unprecedented levels of long-term thinking and commitment. They'll need to survive economic downturns, political changes, and the natural human tendency to lose interest in projects that don't show immediate results. The space industry is already proving that such long-term commitment is possible. Companies like SpaceX have been working toward Mars colonization for over 2 decades, maintaining focus and momentum even when the goal seemed impossibly distant. The James Webb Space Telescope took nearly 30 years from initial concept to successful deployment, surviving multiple cancellations, budget crises, and technical setbacks. These examples suggest that we might be developing the institutional resilience needed for interstellar projects. We're learning how to build organizations that can sustain ambitious goals across multiple decades, how to maintain technical expertise across generations of engineers and scientists, how to adapt and evolve projects without losing sight of their ultimate objectives. But there's another factor that might be even more important than technology or institutional capability. We're discovering compelling reasons why we might need to leave our solar system. Not just because we want to explore, but because we might not have a choice. Astronomical surveys are revealing that our galaxy is a more dangerous place than we once thought. Gamma-ray bursts from distant stars could sterilize entire regions of space. Supernovae in our cosmic neighborhood could strip away Earth's ozone layer. Our own sun will eventually expand into a red giant, making Earth uninhabitable. Even more troubling, we're realizing that asteroid impacts, climate change, or other catastrophic events could threaten human civilization long before any of these cosmic disasters occur. From this perspective, interstellar travel isn't just an interesting scientific challenge, it's an insurance policy for the survival of human civilization. If we remain confined to one star system, we remain vulnerable to any number of events that could end our species. But if we can establish self-sustaining colonies around other stars, we create redundancy that could ensure human survival, even if Earth becomes uninhabitable. This existential motivation is already changing how people think about space exploration. Organizations like the Long Now Foundation and the Future of Humanity Institute are seriously studying existential risks and the role that space colonization might play in mitigating them. Billionaires like Elon Musk explicitly cite the need to make humanity a multi-planetary species as motivation for their space ventures. The combination of technological capability, economic opportunity, and existential necessity is creating a perfect storm of motivation for interstellar exploration. We're developing the tools, we're building the institutions, and we're discovering the reasons why we might need to use them. But perhaps the most fascinating aspect of this emerging capability is how it's changing our understanding of what interstellar exploration might actually look like. We're moving away from science fiction visions of massive starships carrying thousands of people toward more realistic scenarios involving smaller, more focused missions that build capability over time. The first true interstellar missions will likely be robotic probes, similar to breakthrough Starshot, but more capable and sophisticated. These missions will teach us about the interstellar environment, test technologies for communication across interstellar distances, and possibly even begin the process of preparing other star systems for eventual human presence. Following these initial probes, we might see waves of increasingly sophisticated missions, automated manufacturing systems that could begin building infrastructure around other stars, biological samples that could begin the process of terraforming potentially habitable worlds, eventually perhaps human crews or uploaded human consciousnesses that could establish permanent settlements. This step-by-step approach makes interstellar exploration seem less like an impossible dream and more like a natural extension of what we're already doing. We're not trying to solve every problem at once. We're building capability systematically, learning from each mission, using each success to enable the next, more ambitious goal. And here's what makes this approach so compelling. We don't need to wait for revolutionary breakthroughs to get started. The technologies we need for the first steps already exist or are in development. We could launch interstellar precursor missions within the next few decades using extensions of current technology. Ion drives, solar sails, and nuclear power sources could carry sophisticated probes to the edge of our solar system and beyond, testing technologies and gathering data that will inform future missions. Each of these missions would teach us something new about the challenges of interstellar travel. They would test our ability to communicate across vast distances, to build systems that operate reliably for decades, to navigate in the space between stars. Most importantly, they would maintain momentum and interest in interstellar exploration, keeping the goal alive in public consciousness while we develop the more advanced technologies needed for human missions. The timeline for all of this remains uncertain. Robotic interstellar missions might be possible within 50 years. Human missions might require a century or more. But what's becoming clear is that the question isn't whether we'll ever leave our solar system. The question is how long it will take and what form that expansion will ultimately take. We're already taking the first steps, even if we don't always recognize them as such. Every advance in space technology, every successful long-duration mission, every new discovery about the nature of our universe is bringing us closer to the day when humans will look up at the night sky from the surface of a world orbiting another star. The journey has already begun. We just don't know yet where it will ultimately take us or what will become along the way. The transformation we're witnessing in our understanding of interstellar travel goes beyond just technological advancement. It's fundamentally changing how we think about time, distance, and what it means to be human. As we stand on the threshold of potentially becoming an interstellar species, we're discovering that the journey itself might be more important than the destination. Consider what happens when we start thinking seriously about missions that could last centuries. We're not just planning space missions anymore. We're designing civilizations. A generation ship traveling to Proxima Centauri wouldn't just be a spacecraft. It would be a complete society with its own culture, economy, government, and social structures that would need to evolve and adapt over the course of the journey. This raises questions that no human society has ever had to confront. How do you maintain cultural continuity across multiple generations of space travel? What happens when the people who arrive at the destination have never seen Earth, have no direct connection to the world their great-grandparents left behind? Are they still human in the same sense we understand the term today? The psychological research being conducted on long-duration space missions is already revealing how profoundly space travel changes human consciousness. Astronauts who spend months aboard the International Space Station report fundamental shifts in how they perceive Earth, humanity, and their place in the universe. They describe a phenomenon called the overview effect, where seeing Earth from space creates a cognitive shift toward greater environmental awareness and a sense of unity with all life on the planet. Now imagine that psychological transformation extended over decades or centuries. The humans who eventually settle around other stars will likely have perspectives and priorities that we can barely comprehend. They'll be shaped by experiences we've never had, challenges we've never faced, and an environment that's utterly alien to anything in human history. This isn't necessarily a problem to be solved. It might be an inevitable part of becoming an interstellar species. Evolution doesn't just apply to biological systems. It applies to cultures, technologies, and ways of thinking. The humans who spread among the stars will necessarily evolve, both biologically and culturally, in response to their new environments. But this evolutionary pressure works both ways. As we prepare for interstellar exploration, we're already changing ourselves in response to the challenge. The technologies we're developing for space exploration are reshaping life on Earth. The international cooperation required for large space projects is creating new models for global collaboration. The long-term thinking necessary for interstellar missions is influencing how we approach problems like climate change and resource management. In a very real sense, becoming an interstellar species is already changing what it means to be human. We're developing capabilities our ancestors never possessed, thinking in timescales that exceed individual lifespans, and taking on challenges that require unprecedented levels of cooperation and commitment. The economic implications of this transformation are equally profound. The space economy is already worth hundreds of billions of dollars and growing exponentially. Companies are making serious money from satellite communications, Earth observation, space tourism, and asteroid mining research. But this is just the beginning. If we successfully develop the technologies needed for interstellar travel, we'll create economic opportunities that dwarf anything in human history. The resources contained in just one asteroid could exceed the entire wealth of nations. The energy sources we'll need for interstellar propulsion could revolutionize how we power our civilization. The manufacturing techniques developed for space-based construction could transform every industry on Earth. But perhaps more importantly, the pursuit of interstellar capabilities is driving innovations that are already changing life on Earth in unexpected ways. The miniaturization required for interstellar probes is advancing computer technology. The life support systems needed for long-duration space missions are improving environmental technology. The communication systems required for interstellar distances are enhancing global connectivity. This pattern of space exploration driving terrestrial innovation has been consistent throughout history. The Apollo program didn't just put humans on the moon, it created technologies that enabled modern computing, advanced materials science, and revolutionized manufacturing. The same pattern is likely to repeat with interstellar exploration, but on an even larger scale. The challenges of interstellar travel are so extreme that solving them will require breakthroughs in virtually every field of human knowledge. Physics, engineering, biology, psychology, sociology, economics, philosophy. Every discipline will need to contribute to making interstellar exploration possible, and every breakthrough we make in service of that goal will have applications that extend far beyond space travel. Consider the energy problem. To accelerate even a small spacecraft to a significant fraction of light speed requires energy sources that are orders of magnitude more powerful than anything we currently possess. Solving this problem will likely require mastering fusion power, developing more efficient solar collection systems, or even learning to harness more exotic energy sources. But these same energy technologies could solve the climate crisis, provide abundant clean power for developing nations, and enable technological capabilities we can barely imagine. The pursuit of interstellar travel could inadvertently solve some of humanity's most pressing problems right here on Earth. The same logic applies to every other challenge we face in interstellar exploration. The closed-loop life support systems needed for generation ships could revolutionize agriculture and environmental management. The artificial intelligence required for autonomous interstellar probes could solve problems in medicine, education, and scientific research. The materials science needed for spacecraft that can survive decades in interstellar space could create stronger, lighter, more durable materials for every application. In essence, the attempt to leave our solar system is already transforming our solar system. We're not just building the capability to reach other stars, we're building the capability to create a better civilization wherever we happen to be. But this raises another fascinating question about the nature of interstellar expansion. If the technologies we develop for interstellar travel make life in our solar system dramatically better, will we still want to leave? Or will our solar system become so abundant, so comfortable, so filled with opportunities that interstellar travel becomes unnecessary. This isn't a rhetorical question. Some futurists argue that advanced civilizations might naturally turn inward rather than expanding outward. If you can create virtual worlds indistinguishable from reality, if you can modify your consciousness to experience any imaginable environment, if you can access unlimited energy and resources within your home star system, why would you bother with the enormous effort and risk of interstellar travel? This possibility, sometimes called the transcension hypothesis, suggests that truly advanced civilizations might focus on intensive development rather than extensive expansion. Instead of spreading across the galaxy, they might create increasingly sophisticated virtual environments, upload their consciousness to digital systems, or even manipulate matter at the quantum level to create whatever experiences they desire. From this perspective, our current dreams of interstellar expansion might be a temporary phase in our development. We might eventually discover that everything we could possibly want to experience or achieve can be accomplished more easily by transforming ourselves and our local environment rather than traveling to distant stars. But even if this turns out to be true, the pursuit of interstellar capability might still be worthwhile. The technologies and perspectives we develop in attempting to become an interstellar species will be valuable regardless of whether we actually need to leave our solar system. The journey toward interstellar capability is already making us more capable, more cooperative, and more conscious of our place in the universe. There's another possibility that's even more intriguing. What if the process of developing interstellar technology reveals that the universe is far more connected than we currently understand? What if the same advances that make interstellar travel possible also reveal new ways to communicate or even travel instantaneously across vast distances? Physics is already hinting at connections that transcend our everyday understanding of space and time. Quantum entanglement allows particles to influence each other instantaneously across any distance. The structure of space-time itself might contain shortcuts that could make interstellar travel far easier than we imagine. The nature of consciousness might turn out to be more fundamental to reality than we currently believe. As we push the boundaries of technology in pursuit of interstellar capability, we might discover that the universe works in ways that make our current challenges obsolete. We might find that consciousness can be transmitted instantaneously across any distance, that space-time can be folded to bring distant stars within easy reach, or that reality itself can be manipulated in ways that eliminate the need for physical travel altogether. These possibilities might sound like science fiction, but they're grounded in serious scientific speculation. Physicists are already exploring concepts like wormholes, warp drives, and quantum teleportation. While these ideas remain highly speculative, they illustrate how our understanding of what's possible continues to evolve as our knowledge deepens. The point isn't that any particular exotic technology will solve the interstellar travel problem. The point is that our current understanding of physics and consciousness is incomplete, and the gaps in our knowledge might contain solutions we haven't yet imagined. This uncertainty is actually one of the most exciting aspects of the interstellar challenge. We're not just trying to solve a well-defined engineering problem. We're pushing into territory where our fundamental assumptions about reality might need to be revised. Every step forward in our capability to explore space is also a step forward in our understanding of the universe itself. And this brings us to perhaps the most profound aspect of the question of whether we'll ever leave our solar system. The answer matters less than the asking. The very process of seriously attempting to become an interstellar species is transforming us in ways that might be more important than actually reaching other stars. We're learning to think in cosmic timescales, to cooperate on projects that exceed individual lifespans, to solve problems that require the combined efforts of multiple disciplines and nations. We're developing technologies that could solve existential problems, perspectives that could help us navigate complex global challenges, and capabilities that could enable entirely new forms of civilization. Whether we eventually establish colonies around Proxima Centauri or Alpha Centauri might be less important than the fact that we're becoming the kind of species capable of seriously attempting such projects. The transformation is already underway, and it's already changing everything about how we understand ourselves and our place in the universe. The children growing up today will live in a world where interstellar missions are not just science fiction, but active engineering projects. They'll think differently about time, space, and human potential, because they'll grow up knowing that humans are actively working to reach other stars. That shift in perspective might be more transformative than any particular technological breakthrough. We're at a unique moment in human history where the impossible is becoming merely difficult. The question of whether we'll ever leave our solar system is evolving from philosophical speculation to practical planning. And regardless of how that planning ultimately unfolds, the very fact that we're taking it seriously is already changing what it means to be human. The universe is vast, ancient, and filled with wonders we're only beginning to imagine. Whether we explore it by sending our bodies, our minds, or our creations across interstellar distances, the exploration itself is expanding our consciousness, our capabilities, and our understanding of what's possible. We may not yet know whether we'll ever leave our solar system, but we're discovering that asking the question seriously is already taking us places we've never been before. And perhaps that's the most important journey of all. The next few decades will likely determine not just whether interstellar travel is possible, but what form it will take and how it will transform us along the way. We're not just building spaceships, we're building the future of human consciousness itself. And that future is arriving faster than most people realize. The technologies, institutions, and perspectives we need for interstellar exploration are already under development. The only question remaining is how quickly we can bring them together into a coherent program for expanding beyond our solar system. The answer to that question will determine not just where humanity goes next, but what humanity becomes in the process of getting there. The timeline we're looking at for this transformation is both thrilling and sobering. Conservative estimates suggest that meaningful interstellar missions, even robotic ones, are still decades away. But here's what's remarkable about our current moment in history. We're living through the foundational years of what could become humanity's greatest adventure. The decisions we make today about space exploration funding, international cooperation, and technological priorities will directly determine whether our children or grandchildren witness the first successful interstellar mission. Consider the accelerating pace of change in space technology. Just 20 years ago, the idea of reusable rockets was considered impractical by most experts. Today, SpaceX routinely lands rockets back on Earth and reuses them for multiple missions. The James Webb Space Telescope, launched just a few years ago, is already revolutionizing our understanding of distant worlds and the conditions that might support life around other stars. Private companies are seriously planning missions to asteroids, the Moon, and Mars, with timelines that seemed impossibly aggressive just a decade ago. This acceleration isn't just about individual technologies improving. It's about entire technological ecosystems reaching maturity simultaneously. Artificial intelligence is approaching levels of sophistication that could enable truly autonomous spacecraft operations. Advanced materials, science is producing substances that are stronger, lighter, and more radiation resistant than anything previous generations could imagine. Energy storage and generation technologies are becoming more efficient and compact every year. But perhaps most importantly, we're witnessing the emergence of a space-focused economy that could eventually support the massive investments required for interstellar missions. When companies can make money from space tourism, asteroid mining, and orbital manufacturing, they create the economic foundation that could eventually fund far more ambitious projects. The space economy isn't just growing, it's becoming self-sustaining in ways that government-funded programs never could. This economic transformation is crucial because interstellar missions will require investment levels that exceed what any single nation could reasonably commit to. But if space-based industries become profitable enough, if the potential returns from interstellar exploration become clear enough, private capital might eventually flow toward these projects, just as it flows toward any other promising investment opportunity. The psychological barriers to interstellar exploration are proving to be just as significant as the technological ones. Human beings evolved to care most about immediate threats and opportunities. Our brains are wired to focus on problems we can solve within our lifetimes, challenges that affect our families and communities directly. Asking people to commit resources to projects that might take centuries to complete goes against some of our deepest psychological instincts. Yet we're already seeing signs that this psychological barrier isn't insurmountable. Climate change has taught us to think in longer timescales, to consider problems that might affect our children and grandchildren rather than just ourselves. The COVID-19 pandemic showed us how quickly human societies can mobilize resources and change behavior when faced with existential threats. The space industry has demonstrated that people will invest in projects with uncertain timelines if the potential returns are significant enough. More intriguingly, younger generations seem naturally more comfortable with long-term thinking and global cooperation than their predecessors. People who grew up with the internet, who communicate routinely with individuals on other continents, who see images from Mars rovers and space telescopes as part of their daily news cycle, approach questions about interstellar exploration with a fundamentally different mindset than previous generations. These psychological shifts might be just as important as technological advances in making interstellar missions possible. If enough people genuinely believe that human expansion beyond our solar system is both necessary and achievable, the social and political support for such projects becomes much more likely. The scientific discoveries we're making about other star systems are also changing the conversation in profound ways. Every new exoplanet we discover, every potentially habitable world we identify around nearby stars, makes the case for interstellar exploration more compelling. We're not just talking about sending probes into empty space anymore. We're talking about investigating specific worlds that might harbor life, that might be suitable for human habitation, that might hold answers to fundamental questions about the nature and prevalence of life in the universe. The Kepler Space Telescope and its successors have revealed that planets are incredibly common throughout our galaxy. Nearly every star we can observe has at least one planet orbiting it, and many of these worlds fall within the temperature ranges where liquid water could exist. Some of these potentially habitable planets orbit stars that are very close to us in astronomical terms. Proxima Centauri b, just over 4 light-years away, might have conditions suitable for life. TRAPPIST-1, about 40 light-years distant, hosts multiple Earth-sized worlds in its habitable zone. These discoveries transform interstellar exploration from abstract scientific curiosity to concrete investigation of specific targets. We're not just asking whether we can build machines capable of reaching other stars. We're asking whether we can build machines capable of studying potentially habitable worlds that we know exist around those stars. The biological implications of interstellar travel are becoming clearer as we learn more about how space affects human physiology. Long-duration missions aboard the International Space Station are teaching us about bone density loss, muscle atrophy, radiation exposure, and psychological stress in ways that directly inform planning for interstellar journeys. We're discovering which problems can be solved with current technology and which will require fundamental breakthroughs. Some of the challenges are more manageable than we initially feared. Artificial gravity generated by rotating spacecraft sections could eliminate many of the bone and muscle problems associated with weightlessness. Advanced shielding materials could protect crews from most forms of radiation. Closed-loop life support systems are already being tested that could theoretically sustain crews for decades without resupply. Other challenges are proving more intractable. The psychological stress of permanent separation from Earth, the social dynamics of small groups confined together for extended periods, the medical challenges of treating serious illnesses without possibility of evacuation. These human factors might ultimately prove more limiting than any technological constraint. But even these seemingly insurmountable problems are driving innovations that extend far beyond space exploration. Research into psychological resilience for space crews is advancing our understanding of mental health in extreme environments. Work on medical systems for interstellar missions is pushing the boundaries of automated surgery and diagnostic equipment. Studies of social dynamics in isolated groups are revealing principles that apply to everything from military units to corporate teams. The philosophical implications of interstellar exploration are perhaps the most profound of all. If we successfully establish human settlements around other stars, we'll be creating the first truly independent human societies in history. Every previous human expansion, from the settlement of remote islands to the colonization of new continents, has maintained some connection to the broader human community. But interstellar colonies would be genuinely isolated, forced to develop their own solutions to fundamental questions about governance, economics, culture, and meaning. This independence isn't just practical, it's existential. The humans who settle around other stars will face challenges and opportunities that no one on Earth has ever experienced. They'll need to develop new ways of thinking about identity, community, and purpose. Over time, they might evolve culturally and even biologically in directions we can't predict. This prospect of human diversification across multiple star systems raises questions that touch on the deepest aspects of what it means to be human. Will the descendants of interstellar colonists still consider themselves human in the same sense we do? Will they maintain connections to Earth-based humanity? Or will they develop into something genuinely new? Are we looking at the next step in human evolution, or the beginning of multiple human species? These aren't just philosophical abstractions. They're practical questions that will need answers if we're serious about interstellar colonization. How do we maintain communication and cooperation between human settlements separated by light years? How do we prevent interstellar colonies from developing into threats to Earth or each other? How do we ensure that the expansion of humanity beyond our solar system serves the interests of all human beings, not just those wealthy or fortunate enough to participate directly? The governance challenges alone are staggering. What legal frameworks apply to interstellar colonies? Who has jurisdiction over human settlements around other stars? How do we prevent the same patterns of exploitation and conflict that have characterized human expansion throughout history from repeating themselves on an interstellar scale? These questions are becoming more than academic as space law evolves to address the realities of commercial space exploration. The legal frameworks we develop for asteroid mining, lunar settlements, and Mars colonies will likely serve as precedents for interstellar governance. We're essentially writing the constitution for human expansion beyond Earth, even though we don't fully realize it yet. The environmental implications of becoming an interstellar species are equally complex. On one hand, spreading human civilization across multiple star systems could serve as the ultimate backup plan for preserving both human culture and Earth's biological heritage. If catastrophe strikes our home planet, interstellar colonies could ensure that the legacy of Earth-based life continues elsewhere in the galaxy. On the other hand, interstellar expansion could also represent the ultimate environmental impact. If we carry Earth life to other star systems, we might be contaminating pristine environments that have followed completely different evolutionary paths for billions of years. We might be imposing Earth-based biology on worlds that harbor their own unique forms of life. These concerns are already shaping how we plan even robotic missions to other stars. Planetary protection protocols are being developed to minimize the risk of contaminating potentially habitable worlds with Earth-based microorganisms. But the ethical questions become far more complex when we're talking about deliberate colonization efforts, rather than just scientific exploration. Do we have the right to establish human settlements on worlds that might harbor indigenous life? How do we balance human expansion needs against the preservation of alien ecosystems? What responsibilities do we have to future generations of both humans and potential alien life forms? The answers to these questions will likely determine not just whether we leave our solar system, but how we do it, and what kind of interstellar civilization we create in the process. The choices we make about these issues will define the character of humanity's cosmic future for potentially millions of years. But perhaps the most remarkable aspect of our current situation is how rapidly our perspective on these questions is evolving. Ideas that seemed like pure science fiction just decades ago are now subjects of serious academic research and policy discussion. Graduate students are writing dissertations on interstellar mission design. Government agencies are funding research into technologies that could enable interstellar exploration. Private organizations are investing real money in projects specifically designed to advance interstellar capabilities. This shift from speculation to serious planning represents a fundamental change in how humanity sees itself and its future. We're no longer just a species that happens to live on one planet. We're beginning to see ourselves as a species with the potential to spread throughout the galaxy, to become a truly cosmic civilization. That transformation in self-perception might be the most important factor in determining whether we actually achieve interstellar capabilities. People who see interstellar expansion as an inevitable part of human development will make different choices, support different policies, and invest in different technologies than people who see it as an impossible dream. The generation that's growing up today will be the first to make major life decisions with the genuine possibility of interstellar missions in their lifetimes. Some of them will choose careers in space technology specifically because they want to contribute to interstellar exploration. Some will support political candidates based partly on their positions on space exploration funding. Some will make investment decisions with interstellar commercial opportunities in mind. These individual choices, multiplied across millions of people, will collectively determine whether we develop the social, economic, and technological infrastructure needed for interstellar missions. The future of interstellar exploration isn't just being determined in government laboratories and corporate boardrooms. It's being shaped by the choices that ordinary people make every day about what kind of future they want to support. And those choices are being influenced by our growing understanding of just how extraordinary and precious our situation really is. The more we learn about the universe, the more we realize how remarkable it is that complex life evolved on Earth at all. The conditions that allowed for the development of intelligence, technology, and civilization represent an almost impossibly unlikely convergence of factors. This realization creates both urgency and responsibility around the question of interstellar expansion. If intelligent life is as rare as it appears to be, then we might have obligations that extend far beyond our own species. We might be responsible not just for ensuring human survival, but for preserving and spreading the phenomenon of consciousness itself throughout the galaxy. From this perspective, interstellar exploration isn't just about human expansion or scientific curiosity. It's about ensuring that the universe continues to have conscious beings capable of appreciating its beauty, understanding its complexity, and perhaps even improving upon its natural processes. Whether we'll ever leave our solar system might ultimately depend on whether we can embrace this level of cosmic responsibility. If we can see ourselves not just as one species among many, but as the universe's best current hope for conscious exploration and understanding, we might find the motivation and resources needed to make interstellar expansion not just possible, but inevitable. The question isn't really whether we'll ever leave our solar system. The question is whether we'll choose to become the kind of species capable of doing so responsibly, sustainably, and in service of something larger than our immediate self-interest. That choice is being made right now, in the decisions we make about science funding, international cooperation, environmental protection, and technological development. Every choice that expands human capability, promotes long-term thinking, or advances our understanding of the universe, brings us closer to becoming an interstellar civilization. The transformation has already begun. We just don't know yet how far it will take us, or what we'll discover about ourselves and the universe along the way. The most fascinating aspect of our current trajectory toward interstellar capability is how it's revealing that the universe itself might be actively encouraging conscious beings to spread throughout the galaxy. As we develop more sophisticated telescopes and detection methods, we're discovering that the cosmos is structured in ways that seem almost designed to facilitate the expansion of intelligence across interstellar distances. Consider the distribution of potentially habitable worlds around nearby stars. Rather than being randomly scattered throughout the galaxy, many of the most promising targets for interstellar missions are clustered within a relatively small region of space around our solar system. Proxima Centauri, just over 4 light-years away, hosts a potentially Earth-like planet. The TRAPPIST-1 system, 40 light-years distant, contains multiple worlds that could support liquid water. Wolf 359, Barnard Star, and dozens of other nearby systems show signs of planetary companions that might harbour conditions suitable for life. This clustering isn't coincidental. It reflects the fact that stars in our region of the galaxy formed from similar materials at roughly the same time, creating environmental conditions that favour the development of rocky planets in habitable zones. We're not just randomly distributed in space. We're part of a stellar neighbourhood where the conditions that gave rise to Earth and potentially to life itself are relatively common. This realization is transforming how we think about interstellar expansion strategies. Instead of viewing interstellar travel as a series of individual, isolated missions to distant and unknown destinations, we're beginning to see it as a systematic exploration of a cosmic region that's naturally suited to supporting the kind of life and intelligence that developed on Earth. The implications are profound. If we can successfully establish even one self-sustaining human settlement around another star, that colony could serve as a stepping stone for further expansion throughout our local stellar neighborhood. Each successful settlement would provide a base for exploring and potentially colonizing other nearby systems, creating a cascading effect that could lead to human presence throughout dozens or even hundreds of star systems within a few millennia. But this cascading expansion model depends critically on our ability to develop what we might call reproductive space technology. Just as biological life spreads by reproducing itself, interstellar civilization would need to spread by reproducing its technological and social infrastructure in new locations. This means that our first interstellar missions can't just be about sending people to other stars. They need to be about sending the capability to build, maintain, and expand technological civilization using resources found in those distant systems. This requirement is driving some of the most innovative thinking in current space technology development. Researchers are working on self-replicating manufacturing systems that could use raw materials from asteroids, planets, or even interstellar space to build copies of themselves. Others are developing biological systems that could terraform planetary environments, creating Earth-like conditions around other stars. Still others are exploring how artificial intelligence systems could serve as the seed for rebuilding human civilization in locations where direct human presence isn't initially feasible. The concept of self-replicating space technology sounds like science fiction, but it's grounded in solid engineering principles. We already have crude versions of this capability in our industrial base on Earth. Modern manufacturing systems can produce copies of themselves given sufficient raw materials and energy. Biological organisms demonstrate that self-replication is not only possible, but can be incredibly sophisticated and efficient. The challenge is adapting these principles to work in the extreme environments of interstellar space and alien worlds. Self-replicating systems need to be robust enough to function reliably for decades or centuries without human intervention. They need to be flexible enough to adapt to environments that might be completely different from anything they were originally designed for. And they need to be sophisticated enough to eventually produce not just copies of themselves, but the entire technological infrastructure needed to support human civilization. Some researchers are approaching this challenge by developing what they call universal constructors, manufacturing systems so flexible and capable that they can theoretically build anything, including copies of themselves, given appropriate raw materials and instructions. These systems would combine advanced robotics, artificial intelligence, and nanotechnology to create manufacturing capability that could function in virtually any environment. Others are exploring biological approaches, engineering organisms that could serve as the foundation for terraforming other worlds. These biological systems would be designed to survive in alien environments, while gradually transforming those environments to become more suitable for Earth-based life. Over time, they could create the atmospheric and ecological conditions needed to support human settlements. The most ambitious proposals combine both approaches, envisioning missions that would send both technological and biological systems to other star systems. The technological systems would build the infrastructure needed for human habitation, while the biological systems would create the environmental conditions needed to support that infrastructure over the long term. But perhaps the most intriguing possibility is that our first successful interstellar colonies won't be purely human at all. They might be hybrid civilizations that combine human consciousness with artificial intelligence, biological engineering, and technological systems in ways that are optimized for survival and expansion in interstellar environments. This possibility is already being explored in research on human-machine interfaces, genetic engineering, and artificial intelligence. If we can successfully merge human intelligence with artificial systems, if we can engineer biological systems to thrive in alien environments, if we can create technological infrastructure that maintains itself indefinitely, then we might be able to create forms of civilization that are far better suited to interstellar expansion than anything purely human could ever be. These hybrid civilizations would still be recognizably human in their origins and values, but they would be adapted to thrive in environments where unmodified humans couldn't survive. They would represent the next step in human evolution, shaped not by natural selection on Earth, but by the conscious choice to adapt ourselves to the cosmos. The timeline for developing these capabilities remains uncertain, but the underlying technologies are advancing rapidly. Artificial intelligence is approaching levels of sophistication that could enable truly autonomous systems. genetic engineering is becoming precise enough to design organisms for specific environments. Robotics and manufacturing technology are becoming flexible enough to work with a wide variety of materials and conditions. More importantly, these different technological streams are beginning to converge in ways that suggest breakthrough capabilities might emerge sooner than many experts expect. The same artificial intelligence systems that could enable autonomous interstellar probes could also control self-replicating manufacturing systems. The same genetic engineering techniques that could create organisms for terraforming could also enhance human capability for long-duration space travel. The same robotics technology that could build infrastructure on alien worlds could also maintain and repair spacecraft during interstellar journeys. This technological convergence is being accelerated by the economic incentives created by the emerging space economy. Companies that develop better artificial intelligence, more flexible manufacturing systems, or more robust biological engineering don't just gain advantages in space exploration. They gain advantages in terrestrial markets that are already worth hundreds of billions of dollars annually. The result is a feedback loop, where advances in space technology drive advances in terrestrial technology, which generate profits that fund further advances in space technology. This cycle is accelerating as the space economy grows and as the potential returns from interstellar exploration become clearer. But the most remarkable aspect of this technological convergence is how it's changing our understanding of what interstellar expansion might actually look like. We're moving away from science fiction images of massive starships carrying thousands of people toward more realistic scenarios involving waves of increasingly sophisticated robotic missions that gradually build the infrastructure needed to support human presence around other stars. The first wave might consist of small, highly advanced probes, similar to those proposed by breakthrough Starshot, but with more sophisticated sensors and communication systems. These probes would map the environments around target stars, identify the most promising worlds for further exploration, and begin the process of characterizing the resources available in those systems. The second wave might include larger robotic missions equipped with self-replicating manufacturing capability. These missions would use resources found in the target systems to build communications infrastructure, energy collection systems, and basic manufacturing facilities. They would essentially establish the technological foundation needed to support more complex operations. The third wave might introduce biological systems designed to begin the process of environmental modification. These could include engineered microorganisms that could alter planetary atmospheres, organisms designed to break down local materials into forms useful for human technology, or even more complex biological systems that could begin creating Earth-like ecosystems on suitable worlds. Only after these preparatory waves had successfully established the necessary infrastructure would human beings, in whatever form they might take by then, make the journey to other stars. By that point, they would be arriving not as pioneers venturing into unknown territory, but as the final component of a carefully planned colonization effort that had been decades or centuries in preparation. This staged approach to interstellar expansion makes the timeline much more manageable and the technical challenges much more solvable. Instead of trying to solve every problem at once, we can focus on developing and deploying each wave of technology as it becomes available, learning from each stage to improve the next. The economic model for this kind of expansion is also becoming clearer. Each wave of interstellar missions would be funded by the value created by previous waves. The first robotic probes would generate scientific and technological knowledge that has value back on Earth. The manufacturing infrastructure established by later missions would produce materials and products that could be valuable for further space exploration. Eventually, the resources and capabilities developed around other stars could become economically valuable in their own right. This economic sustainability is crucial because interstellar expansion will require investment levels that exceed what governments can reasonably commit to indefinitely. But if each stage of the process creates value that can fund subsequent stages, then interstellar expansion becomes not just technically feasible, but economically inevitable. The social and political implications of this staged expansion model are equally fascinating. Instead of requiring massive upfront commitments to uncertain projects, it allows for gradual increases in capability and commitment as each stage proves successful. Public and political support can build organically as people see concrete progress and tangible benefits from each phase of the expansion process. This approach also allows for much more international cooperation than traditional models of interstellar exploration. Different nations or organizations can contribute to different phases of the expansion process, sharing both costs and benefits in ways that reflect their capabilities and interests. The result could be interstellar expansion that truly represents the best of human civilization, rather than just the ambitions of a few wealthy nations or individuals. But perhaps the most important aspect of this staged approach is how it addresses the fundamental question of motivation. Why would human beings commit to projects that might take centuries to complete and offer no direct benefit to themselves? The staged approach transforms this question by making each phase valuable in its own right, while also contributing to the larger goal of interstellar expansion. The first robotic probes will advance our scientific understanding and technological capabilities in ways that benefit everyone on Earth immediately. The infrastructure built by subsequent missions will create new economic opportunities and scientific capabilities that justify their cost regardless of their contribution to interstellar expansion. The environmental modification efforts will teach us techniques that could be valuable for managing Earth's environment, as well as creating new habitats around other stars. Each stage creates immediate value while also advancing the longer-term goal of establishing human presence around other stars. This makes it much easier to maintain public support and political commitment across the decades or centuries required for successful interstellar expansion. The result is a vision of interstellar expansion that feels not just technically feasible, but socially and economically sustainable. We're not asking current generations to sacrifice for benefits they'll never see. We're proposing a series of projects that create value for current generations, while also building the capability for future generations to expand beyond our solar system if they choose to do so. This approach also addresses many of the ethical concerns about interstellar expansion. Instead of rushing to establish human colonies that might contaminate alien environments, the staged approach allows for careful study of target systems before any irreversible commitments are made. If we discover indigenous life around other stars, we can modify our expansion plans to protect those ecosystems. If we find that certain worlds are unsuitable for human habitation, we can redirect our efforts toward more promising targets. The flexibility built into this approach means that interstellar expansion can adapt to whatever we discover about the universe as our capabilities improve. We're not locked into any particular vision of what interstellar civilization should look like. Instead, we're building the capability to pursue whatever opportunities turn out to be most promising and most consistent with our evolving values and understanding. This adaptive approach to interstellar expansion reflects a broader shift in how we think about humanity's cosmic future. We're moving away from rigid plans based on current assumptions toward flexible strategies that can evolve as our knowledge and capabilities improve. We're recognizing that the universe is likely to surprise us in ways we can't anticipate, and we're designing our expansion efforts to take advantage of those surprises, rather than being derailed by them. The next few decades will likely determine whether this vision of staged, sustainable interstellar expansion becomes reality or remains an unrealized possibility. The technologies we develop, the institutions we build, and the choices we make about international cooperation and resource allocation will all influence whether we successfully begin the first phase of systematic expansion beyond our solar system. But regardless of how quickly we progress, the very fact that we're seriously planning for interstellar expansion is already changing us in profound ways. We're developing the long-term thinking, international cooperation, and technological sophistication that could enable us to become a truly cosmic civilization. And those capabilities are valuable, regardless of whether we ultimately use them to reach other stars or to build a better civilization within our own solar system. The question of whether we'll ever leave our solar system is evolving from philosophical speculation to practical planning. And that transformation, more than any particular technological breakthrough, might be the most important step we take toward becoming an interstellar species. The question of whether humanity will ever leave our solar system is becoming less about possibility and more about inevitability, but not for the reasons most people imagine. As we stand at this remarkable intersection of technological capability and cosmic awareness, we're discovering that our expansion beyond the sun's influence might not be driven by wanderlust or scientific curiosity alone. It might be driven by necessity, by opportunity, and by forces we're only beginning to understand. Consider what's happening right now in laboratories and research facilities around the world. Scientists are making discoveries about the nature of space itself that could fundamentally alter how we think about interstellar travel. The vacuum of space, once thought to be empty, is revealing itself to be a dynamic medium filled with energy fluctuations, particle interactions, and phenomena that might be harnessed for propulsion. Theoretical physicists are exploring concepts like the Alcubierre drive, which wouldn't move a spacecraft through space at all, but would instead contract space in front of the vehicle and expand it behind, creating a bubble of warped space-time that could theoretically travel faster than light without violating relativity. These aren't just mathematical curiosities anymore. Research groups are conducting actual experiments to test whether space-time manipulation might be achievable with technologies we could develop in the coming decades. The results are preliminary. The energy requirements remain staggering, but the mere fact that serious scientists are pursuing these investigations represents a fundamental shift in how we approach the interstellar challenge. Meanwhile, advances in quantum mechanics are revealing connections between consciousness, information, and the structure of reality that could open entirely new pathways for interstellar exploration. If consciousness turns out to be more fundamental to the universe than we currently understand, if information can be transmitted or reconstructed across vast distances through quantum entanglement, then the nature of what it means to travel to other stars might be completely different from our current assumptions. Imagine being able to scan and digitize human consciousness with sufficient precision that the information pattern that constitutes your mind could be transmitted at the speed of light to a receiver around another star. The physical journey would still take years, but from your subjective experience, you would simply close your eyes in one location and open them in another. Your body might be artificially constructed from local materials at the destination, but your consciousness, your memories, your essential self would remain continuous. This possibility pushes us into territory where science and philosophy merge, where questions about the nature of identity and existence become as important as questions about rocket fuel and radiation shielding. But the underlying technologies that might make such scenarios possible are advancing rapidly. brain imaging is reaching resolutions that allow researchers to map individual neurons and their connections. Artificial intelligence is approaching levels of sophistication where it might be possible to simulate consciousness in digital form. Quantum computing is revealing new ways to process and transmit information that transcend classical limitations. Even if consciousness uploading proves impossible or undesirable, the same advances in understanding the relationship between mind and matter are opening up other possibilities for interstellar exploration. Enhanced human beings, modified to survive the rigors of interstellar travel, could be designed with extended lifespans, improved radiation resistance, and psychological adaptations that make decades-long journeys not just survivable, but fulfilling. The biological technologies needed for such enhancements are developing alongside the physical technologies for interstellar propulsion. Gene editing is becoming precise enough to make targeted modifications to human physiology. Synthetic biology is learning to design organisms from scratch for specific environments and purposes. Nanotechnology is approaching the capability to repair and maintain biological systems at the molecular level. These advances suggest that the humans who eventually travel to other stars might be fundamentally different from the humans alive today. Not because they'll be forced to adapt to alien environments, but because they'll choose to optimize themselves for the unique challenges and opportunities of interstellar exploration. They might live longer, think differently, and experience reality in ways that are enhanced compared to our current biological limitations. But perhaps the most intriguing development in our approach to interstellar exploration is the growing recognition that we might not need to solve the distance problem at all. Instead of bringing human beings to other stars, we might eventually bring other stars closer to us. Not physically, of course, but through technologies that allow us to manipulate space and time in ways that effectively reduce the distances involved. Wormholes, those hypothetical tunnels through space-time that could connect distant regions of the universe, remain purely theoretical. But the mathematics that describe them are consistent with our current understanding of physics, and some researchers are exploring whether such structures might be created artificially or whether natural wormholes might exist and be detectable. Even more speculative are proposals for manipulating the fundamental constants of physics within localized regions of space. If the speed of light could be increased within a spacecraft's immediate vicinity, or if time could be dilated in ways that make long journeys pass quickly from the traveler's perspective, then interstellar exploration might become as routine as intercontinental travel is today. These possibilities remain far beyond our current technological capabilities, but they illustrate how rapidly our understanding of what might be possible continues to evolve. Each new discovery in fundamental physics opens up potential applications that previous generations couldn't have imagined. The same pattern that gave us nuclear power, lasers, and computer technology from advances in quantum mechanics might eventually give us interstellar travel capabilities from advances in our understanding of space-time, consciousness, and the relationship between information and reality. What's particularly fascinating about our current situation is how these various technological streams are beginning to converge in unexpected ways. Artificial intelligence research is informing our understanding of consciousness and cognition. Quantum computing is revealing new approaches to information processing that might apply to brain function. Advances in material science are creating substances that could serve as both spacecraft components and biological enhancement materials. This convergence is being accelerated by economic incentives that extend far beyond space exploration. The same technologies that might enable interstellar travel are creating new industries, solving pressing problems on Earth, and generating returns on investment that fund further research and development. We're not just building capabilities for interstellar exploration, We're building capabilities that transform every aspect of human civilization. The timeline for when these converging technologies might enable practical interstellar missions remains uncertain. But the pace of progress is accelerating in ways that consistently surprise experts. Developments that were predicted to take decades are happening in years. Capabilities that seemed impossible just a few years ago are becoming routine parts of our technological landscape. Consider how our relationship with artificial intelligence has evolved in just the past few years. Systems that can engage in sophisticated conversations, create original art and literature, and solve complex problems are becoming commonplace. These same systems are being applied to spacecraft design, mission planning, and the autonomous operation of complex systems in space. The artificial intelligence that might eventually pilot interstellar missions is already being tested and refined in applications much closer to home. Similarly, our ability to manipulate matter at the molecular and atomic levels is advancing at unprecedented rates. Nanotechnology that once existed only in theoretical papers is now being used to create materials with properties that seem almost magical. Self-assembling structures, programmable matter, and molecular machines are transitioning from laboratory curiosities to practical applications. These advances are particularly relevant to interstellar exploration because they address some of the most fundamental challenges of long-duration space missions. Spacecraft that can repair and maintain themselves, materials that can adapt their properties to changing conditions, and manufacturing systems that can create whatever is needed from available resources could make interstellar missions far more feasible than current technologies would suggest. But beyond the technological capabilities, we're also developing the social and institutional frameworks that could support interstellar exploration projects. The same international cooperation that's making the International Space Station and large-scale scientific collaborations possible is creating precedents for the kind of global coordination that interstellar missions would require. Private space companies are demonstrating that ambitious space projects can be sustained and scaled through commercial incentives rather than just government funding. The space economy is creating revenue streams that could eventually support much more ambitious projects than anything government agencies could fund independently. Most importantly, younger generations are growing up with fundamentally different assumptions about what's possible and what's worth pursuing. People who have never known a world without space stations, Mars rovers, and routine commercial space flights approach questions about interstellar exploration with a sense of possibility rather than impossibility. This generational shift in perspective might be the most important factor in determining whether we actually achieve interstellar capabilities. Technical challenges can be solved with sufficient time and resources, but only if there's sustained social and political support for solving them. That support is most likely to come from people who see interstellar exploration not as science fiction, but as a natural extension of capabilities we're already developing. The children who are growing up today will be the ones making major decisions about resource allocation, research priorities, and international cooperation in the coming decades. If they see interstellar exploration as both desirable and achievable, they'll make choices that support its development. If they see it as unnecessary or impossible, they'll direct their attention and resources elsewhere. The stories we tell ourselves about humanity's cosmic future are therefore not just philosophical abstractions. They're practical factors that influence real-world decisions about everything, from education policy to research funding to international agreements about space exploration. This is why the question of whether we'll ever leave our solar system is so important, regardless of what the ultimate answer turns out to be. The very process of seriously considering the question is shaping how we understand ourselves, our capabilities, and our responsibilities as conscious beings in a vast and mysterious universe. We're discovering that becoming the kind of species capable of interstellar exploration requires us to become better at everything, more cooperative, more patient, more technically sophisticated, more environmentally responsible, and more conscious of our long-term impact on the cosmos. These improvements are valuable whether or not we ever actually travel to other stars. The pursuit of interstellar capability is therefore not just about reaching distant destinations. It's about reaching higher levels of human potential. It's about becoming worthy of the cosmic stage on which we find ourselves performing. And in that sense, we're already succeeding. The technologies we're developing, the institutions we're building, the perspectives we're gaining, and the cooperation we're achieving in pursuit of interstellar exploration are already transforming human civilization in profound and positive ways. Whether we'll ever leave our solar system remains an open question, but we're already becoming the kind of species that could do so responsibly and successfully. And that transformation might be the most important journey of all, regardless of where it ultimately takes us among the stars. The future of human expansion beyond our solar system won't be determined by any single breakthrough or decision. It will emerge from the accumulated choices of billions of people over the coming decades, each contributing their skills, resources, and dreams to the collective human project of understanding and exploring our cosmic environment. That project is already underway, accelerating with each passing year, carrying us toward possibilities that seemed impossible just a generation ago. The question isn't whether we're capable of leaving our solar system. The question is what we'll discover about ourselves and the universe in the process of trying. The answer to that question is already being written in the choices we make today, in the technologies we pursue, and in the dreams we're bold enough to imagine into reality. And as we'll discover, those choices are revealing something extraordinary about the nature of human consciousness itself. There's something happening right now that most people don't fully grasp. While we've been debating whether interstellar travel is possible, whether we have the technology or the resources or the motivation to reach other stars, something much more profound has been taking place. We've been transforming ourselves into the kind of beings who ask these questions seriously. And that transformation might be more important than any rocket we could ever build. Think about it for a moment. You're listening to these words, contemplating journeys that would span centuries, considering technologies that manipulate the very fabric of space and time, imagining futures where human consciousness itself might travel between stars at the speed of light. Your ancestors, just a few generations ago, couldn't have conceived of such possibilities, not because they lacked imagination, but because the conceptual framework for thinking about these problems simply didn't exist. We're living through the emergence of what we might call cosmic consciousness, a way of thinking that naturally encompasses stellar distances, geological timescales, and technological possibilities that transcend biological limitations. This isn't just academic knowledge that we acquire through education. It's becoming part of how we instinctively understand our place in the universe. Children today grow up knowing that robots are exploring Mars, that telescopes can see galaxies billions of light years away, that scientists routinely manipulate individual atoms to build new materials. They don't think of these as miraculous achievements. They think of them as the normal baseline of human capability. For them, the question isn't whether we can do extraordinary things. The question is which extraordinary things we should choose to do. This shift in baseline expectations is accelerating in ways that surprise even the experts who study technological development. The same artificial intelligence systems that can engage in sophisticated conversations about physics and philosophy are being integrated into spacecraft design and mission planning. The same genetic engineering techniques that can modify organisms to thrive in extreme environments are being applied to enhancing human capability for long-duration space travel. But perhaps most remarkably, These advances aren't happening in isolation. They're part of an interconnected web of technological and social development that's creating capabilities none of us anticipated. The private space industry that's driving down launch costs is also creating the economic foundation for much more ambitious projects. The international cooperation that's enabling large-scale scientific collaborations is building the institutional frameworks we'll need for interstellar missions. The result is a feedback loop where each advance enables others, where progress in one area accelerates development in seemingly unrelated fields, where the timeline for achieving what once seemed impossible keeps compressing in ways that confound our expectations. Consider how our understanding of what constitutes an interstellar mission has evolved just in the past few years. We've moved from thinking about massive generation ships carrying thousands of people on century-long voyages to considering fleets of tiny, intelligent probes that could reach nearby stars within decades. We've shifted from assuming that interstellar travelers would need to carry everything they need for the journey to realizing that they might be able to manufacture whatever they need from resources found along the way. These aren't just changes in engineering approach. They represent fundamental shifts in how we think about consciousness, identity, and what it means to be human in a cosmic context. If intelligence can be distributed across multiple platforms, if consciousness can be backed up and restored, if human capability can be enhanced through technological integration, then the very nature of what travels between stars becomes fluid and adaptable. The implications ripple through every aspect of how we approach the interstellar challenge. Mission planners are no longer just designing spacecraft and life support systems. They're designing new forms of civilization that can adapt to environments and challenges we've never encountered. They're creating frameworks for maintaining human culture and values across distances and timescales that dwarf anything in our historical experience. But this expansion of possibility is also creating new categories of responsibility. If we develop the capability to spread human presence throughout the galaxy, we also inherit obligations to use that capability wisely. The same technologies that could enable interstellar colonization could also cause irreversible damage to alien ecosystems or create conflicts that span multiple star systems. The ethical frameworks we develop for these unprecedented situations will need to be as sophisticated as the technologies that make them possible. We're essentially writing the moral code for cosmic civilization, establishing principles that could govern human behavior across thousands of star systems over millions of years. These responsibilities extend beyond just avoiding harm. If consciousness and intelligence are as rare in the universe as current evidence suggests, then we might have positive obligations to preserve and spread these phenomena. We might be the universe's best current hope for understanding itself, for appreciating its beauty and complexity, for perhaps even improving upon its natural processes. This possibility transforms interstellar exploration from a matter of human expansion to a cosmic imperative. We're not just carrying our own hopes and dreams to other stars. We're potentially carrying the universe's capacity for self-awareness and conscious experience. The weight of that responsibility is both humbling and inspiring. Yet even as we grapple with these profound questions, the practical work of developing interstellar capabilities continues to accelerate. Laboratory experiments are testing propulsion concepts that could enable spacecraft to reach significant fractions of light speed. Computer simulations are modeling the behavior of materials and systems under the extreme conditions of interstellar travel. Engineering teams are designing manufacturing systems that could function autonomously for decades in deep space. Each of these developments brings us incrementally closer to practical interstellar capability, but their cumulative effect is creating something much more significant than gradual technological progress. They're establishing interstellar exploration as a legitimate field of engineering and scientific inquiry rather than just speculative fiction. Universities now offer courses on interstellar mission design. Government agencies fund research specifically aimed at enabling interstellar capabilities. Private organizations invest real money in technologies that have no application except for missions to other star systems. The infrastructure of knowledge, expertise, and institutional support for interstellar exploration is taking shape even as the ultimate technologies remain under development. This infrastructure is crucial because interstellar missions will require unprecedented levels of coordination across multiple disciplines, institutions, and probably nations. No single organization, no matter how well-funded or technically sophisticated, can master all the technologies needed for successful interstellar exploration. The projects will necessarily be collaborative efforts that draw on the best capabilities available anywhere in human civilization. The precedents for such collaboration already exist in projects like the International Space Station, the Large Hadron Collider, and various international scientific collaborations. But interstellar missions will require cooperation on scales and timelines that exceed anything we've previously attempted. They'll need to survive changes in political leadership, economic conditions, and social priorities across multiple decades or even centuries. Building this kind of institutional resilience requires more than just technical expertise. It requires developing new models of governance, funding, and decision-making that can maintain coherent direction across generational timescales. We're essentially learning how to create organizations that can outlive their founders while staying true to their original mission. The challenge is complicated by the fact that interstellar missions will need to adapt to discoveries and developments that we can't currently anticipate. The technologies we use, the destinations we target, and even the nature of what we send to other stars might change dramatically as our capabilities evolve. The institutional frameworks we create need to be flexible enough to accommodate such changes, while maintaining enough stability to sustain long-term projects. Some researchers are exploring whether artificial intelligence might play a crucial role in providing this institutional continuity. AI systems don't retire, don't change careers, don't lose interest in projects that span decades. They could potentially maintain technical knowledge and institutional memory across timescales that exceed individual human lifespans, serving as a kind of permanent staff for interstellar exploration projects. But even artificial intelligence systems would need to be designed with unprecedented levels of reliability and adaptability. They would need to function flawlessly for decades, while also being capable of learning and evolving as circumstances change. The AI systems that might eventually manage interstellar missions would need to be among the most sophisticated technologies humans have ever created. The development of such systems is already underway in various forms. The autonomous spacecraft that explore our solar system are becoming increasingly capable of independent decision-making. The AI systems that manage complex industrial processes are demonstrating the kind of long-term reliability that interstellar missions would require. The machine learning algorithms that can adapt to new situations and solve novel problems are developing the flexibility that would be essential for missions to unknown environments. These different technological streams are beginning to converge in ways that suggest practical interstellar capability might emerge sooner than most people expect. Not because any single breakthrough will solve all the challenges, but because multiple incremental advances are creating synergistic effects that amplify each other's impact. The result is a technological landscape where the impossible becomes difficult, the difficult becomes routine, and the routine becomes the foundation for achieving things that were previously unimaginable. We're not just developing better rockets or more efficient life support systems. We're creating entirely new categories of technological capability that redefine what kinds of projects are feasible for human civilization. And as these capabilities emerge, they're changing not just what we can do, but what we want to do. The same technologies that make interstellar travel possible also make many other extraordinary projects achievable. We could terraform planets within our own solar system, build massive space-based habitats, or create virtual environments indistinguishable from reality. The question of whether we'll ever leave our solar system is therefore intimately connected to broader questions about what kind of civilization we want to become and what kinds of experiences we want to pursue. If we can create any imaginable environment within our solar system, if we can enhance human consciousness to experience any conceivable reality, if we can solve all the practical problems of energy, resources, and sustainability, then interstellar exploration becomes a choice rather than a necessity. From this perspective, the development of interstellar capability might be less about actually traveling to other stars and more about expanding the range of choices available to future generations. We're creating options that didn't previously exist, enabling forms of human experience and achievement that were previously impossible. Whether future humans choose to exercise those options will depend on their values, interests, and understanding of their situation. But the mere existence of the choices represents a fundamental expansion of human potential and freedom. This expansion of possibility is already influencing how people think about their lives and careers. Young scientists and engineers are choosing to work on projects related to space exploration because they want to contribute to humanity's cosmic future. Entrepreneurs are starting companies focused on space technology because they see enormous opportunities in the emerging space economy. Students are choosing to study physics, engineering, and computer science because they want to be part of developing the technologies that could enable interstellar exploration. These individual choices, multiplied across millions of people, are creating the human capital and institutional momentum that could make interstellar exploration inevitable, regardless of any particular technological breakthrough. We're developing the collective expertise, the economic incentives, and the social support needed to sustain ambitious long-term projects. The transformation is happening at every level of society, from individual career choices to international policy decisions. Space exploration is becoming normalized as a legitimate field of human endeavor rather than an exotic specialty pursued by a small number of specialists. The same cultural shift that made aviation, computing, and telecommunications into major industries is beginning to happen with space technology and exploration. But unlike those previous technological revolutions, the space revolution is happening in the context of global communication networks that allow for unprecedented levels of coordination and collaboration. Researchers working on interstellar propulsion can instantly share their findings with colleagues anywhere in the world. Engineers designing spacecraft systems can collaborate in real time across continents. The development of interstellar capability is becoming a genuinely global project that draws on the best human talent, regardless of nationality or institutional affiliation. This global collaboration is crucial because the challenges of interstellar exploration exceed what any single nation or organization could reasonably tackle alone. The projects require resources, expertise, and perspectives that can only be assembled through international cooperation on unprecedented scales. The precedents for such cooperation are encouraging. The International Space Station has demonstrated that nations can work together effectively on complex technical projects despite political differences. International scientific collaborations have shown that researchers from different countries and cultures can coordinate their efforts to tackle problems that no single group could solve independently. But interstellar missions will require cooperation that extends far beyond anything we've previously attempted. They'll need sustained coordination across decades or centuries through changes in political leadership, economic conditions, and social priorities. They'll need to maintain technical coherence while adapting to discoveries and developments that could fundamentally change the nature of the missions. Creating the institutional frameworks for such cooperation is itself a technological challenge that requires innovation in governance, funding, and decision-making. We're essentially inventing new forms of human organization that can function effectively across timescales and distances that exceed anything in our historical experience. The solutions we develop will likely become models for addressing other global challenges that require long-term thinking and international cooperation. Climate change, resource management, and technological governance all involve similar issues of coordinating action across extended timescales and diverse stakeholder groups. In this sense, the pursuit of interstellar capability is already contributing to human civilization in ways that extend far beyond space exploration. We're developing the institutional technologies needed to function effectively as a global civilization facing complex, long-term challenges. These developments suggest that the question of whether we'll ever leave our solar system is becoming less important than the question of what we're becoming in the process of developing the capability to do so. We're transforming ourselves into a species capable of thinking and acting on cosmic scales, of coordinating complex projects across generational timescales, of taking responsibility for outcomes that extend far beyond our individual lifespans. Whether we ultimately use these capabilities to establish colonies around other stars, or to create an extraordinary civilization within our own solar system, the capabilities themselves represent a fundamental expansion of human potential. We're becoming something new, something unprecedented in the history of our planet, and possibly in the history of our galaxy. The journey toward interstellar capability is therefore not just about reaching distant destinations. It's about reaching new levels of human consciousness, cooperation, and technological sophistication. It's about becoming worthy of the cosmic stage on which we find ourselves performing. And in that transformation lies perhaps the most profound answer to the question of whether we'll ever leave our solar system. We're already leaving, in the sense that we're transcending the limitations that once defined us as a species. We're expanding beyond the boundaries of individual lifespans, national borders, and planetary thinking. The physical journey to other stars might be just one expression of this larger transformation, one application of capabilities we're developing for much broader purposes. But whether or not we ever establish colonies around Proxima Centauri or Alpha Centauri, we're already becoming an interstellar civilization in the ways that matter most. We're thinking like beings who belong among the stars, acting like a species capable of cosmic responsibility, and developing like a civilization worthy of the universe that gave us birth. The question isn't whether we'll ever leave our solar system. The question is, what magnificent forms of existence we'll discover as we become capable of doing so. That discovery is already underway, accelerating with each passing day, carrying us toward possibilities we're only beginning to imagine. The future of human consciousness itself might depend on how courageously we pursue those possibilities and how wisely we choose to use the extraordinary capabilities we're developing along the way. The journey has already begun. We're already traveling among the stars in the ways that matter most, and the destinations we'll ultimately reach might be far more extraordinary than any physical location we could ever visit. The most extraordinary realization about our potential future as an interstellar species is that we're already living in the early chapters of that story, even though most of us don't recognize it yet. Right now, as you contemplate these possibilities, There are technologies being developed in laboratories around the world that will directly enable the first serious attempts at interstellar exploration. Not in some distant science fiction future, but within the next few decades. Consider what's happening in propulsion research at this very moment. Scientists are testing ion drives that can operate continuously for years, gradually accelerating spacecraft to speeds that dwarf anything chemical rockets could achieve. They're developing solar sails that could catch the pressure of starlight itself, riding waves of photons across interstellar space without carrying a single drop of fuel. They're designing fusion rockets that could theoretically reach 10% of light speed, turning 40-year journeys into the realm of practical possibility. But the most fascinating aspect of these developments is how they're converging with advances in artificial intelligence, materials science, and manufacturing technology. The spacecraft that might eventually carry human presence to other stars won't just be faster or more efficient than anything we have today. They'll be fundamentally different in their capabilities, their intelligence, and their ability to adapt to whatever they encounter in the space between stars. These future interstellar missions will likely be conducted by machines that can think, learn, and make decisions with sophistication that rivals or exceeds human intelligence. They'll be equipped with manufacturing systems that can create whatever they need from the raw materials of space itself. They'll carry biological systems that can establish the foundations of Earth-like ecosystems on worlds we've never seen. The timeline for deploying such capabilities remains uncertain, but the underlying technologies are advancing at rates that consistently surprise even the experts working on them. Artificial intelligence systems that were theoretical curiosities just a few years ago are now being integrated into spacecraft design and mission planning. Manufacturing techniques that seemed impossibly futuristic are becoming practical applications for space-based construction projects. What's particularly remarkable is how these advances are being driven not just by government space agencies, but by private companies that see enormous commercial opportunities in space exploration and development. The same economic incentives that built the internet, transformed telecommunications, and created the modern computer industry are now being applied to space technology, with results that are reshaping our understanding of what's possible. The space economy is already worth hundreds of billions of dollars annually and growing at exponential rates. Companies are making real money from satellite services, space tourism, and the development of space-based manufacturing capabilities. This economic foundation is creating the industrial base that could eventually support much more ambitious projects, including the first systematic attempts at interstellar exploration. But beyond the technological and economic developments, something even more profound is happening in how we understand our relationship with the cosmos. We're discovering that the universe itself might be structured in ways that encourage the spread of intelligence and consciousness across interstellar distances. The distribution of potentially habitable worlds around nearby stars, the abundance of the materials needed for technological development, the apparent rarity of intelligent life all suggest that we might have both the opportunity and the responsibility to carry consciousness beyond our solar system. This perspective transforms interstellar exploration from an optional adventure into a cosmic imperative. If we're among the first intelligent species in our region of the galaxy, if consciousness and the capacity for understanding are as rare as they appear to be, then our expansion beyond Earth might represent the universe's best hope for coming to know itself. The weight of that responsibility is both humbling and inspiring. It suggests that the technologies we're developing, the institutions we're building, and the perspectives we're gaining aren't just about human expansion or scientific curiosity. They're about fulfilling a role in cosmic evolution that no other known species has ever played. Whether we rise to meet that challenge will depend on choices we make in the coming decades about research priorities, international cooperation, and the kind of civilization we want to become. The capabilities we're developing give us unprecedented power to shape not just our own future, but the future of consciousness itself in this corner of the galaxy. The question of whether we'll ever leave our solar system is therefore becoming less about technical feasibility and more about wisdom, responsibility, and the courage to embrace our cosmic potential. We're already developing the means. The only question remaining is whether we'll choose to use them in service of something greater than ourselves. That choice is being made right now, in the decisions we make about how to invest our resources, our talents, and our dreams. The future of human consciousness among the stars hangs in the balance, waiting to see whether we'll prove worthy of the extraordinary possibilities that lie before us. The journey to other stars has already begun. The only question is how far we'll choose to go and what we'll discover about ourselves along the way. So here we are, at the end of our cosmic journey together, having travelled from the impossibly vast distances that separate us from our nearest stellar neighbours to the cutting-edge technologies that might one day bridge those gaps. We've explored the seemingly insurmountable challenges of interstellar travel, from the tyranny of the rocket equation to the psychological barriers of multi-generational voyages. We've examined the revolutionary propulsion concepts that could transform science fiction into science fact. And we've discovered that the very act of pursuing these impossible dreams is already changing us in profound ways. The answer to whether we'll ever leave our solar system isn't written in our current rocket technology, or even in the exotic physics we're only beginning to understand. It's being written right now in the choices we make, the dreams we dare to pursue, and the kind of civilization we choose to become. We're already taking those first tentative steps beyond our solar system with probes like Voyager, already developing the international cooperation and long-term thinking that interstellar missions will require, already becoming the kind of species that asks these questions seriously. Perhaps most remarkably, we're discovering that the journey toward interstellar capability might be more transformative than any destination we could ever reach. In learning to think on cosmic scales, to cooperate across generations, and to solve problems that require the best of human ingenuity, we're not just building spacecraft. We're building a better version of ourselves. Whether we ultimately plant human flags around Proxima Centauri or find that our solar system becomes so abundant and fulfilling that we choose to stay, the very possibility of leaving is expanding what it means to be human. The universe is vast beyond imagination, filled with wonders we're only beginning to glimpse. And tonight, as you drift towards sleep under the same stars that have inspired countless generations of dreamers and explorers, remember that you're living through the early chapters of humanity's greatest adventure. The question isn't whether we'll ever leave our solar system. The question is, what magnificent beings we'll become in the process of learning how. Sweet dreams, fellow travelers in this cosmic story. The stars are waiting, and the journey has already begun. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.